Welcome to another video from Lockdown Electronics with me, Bill, and this time we're going to continue our look at operational amplifiers by having a look at a couple of applications where we can use the op-amp to process signals and produce an output which is mathematically related to the inputs. So let's start by taking a look at the first circuit. Okay, first example then is the difference amplifier. Here's the general arrangement of the circuit with the two inputs on the left, output on the right, and you may recall that's got a certain similarity with the inverting amplifier that we looked at in the previous episode, when we were looking at op-amps again, and we've still got R2 at the top there, providing the feedback into the negative going input to get some control over the op-amp's gain. And the only real difference now, of course, is we've got the second input there and with an additional resistor R3. So the mathematics that it does is that the voltage out is equal to the voltage in from 1 minus the voltage in from 2. And so it's going to perform some maths, or math, depending which continent you're on. And the resistors I'm going to use are all 10k here. Doing that gives me a unity gain difference amplifier, which is just good enough for this example. So looking at the breadboard layout, I've taken a slightly oblique view so you get a good view of R2 there, which is that feedback resistor. So all resistors are 10k. I've labelled them up, and you can see the pins out for the bottom half of the op-amp that I'm using, and I'll show you on the breadboard how the inputs and outputs are arranged for us to take some measurements on the scope. Right, let's go and look at that on the breadboard. Here's the difference amplifier set up on the breadboard then. So integrated circuit there, as you can see, resistor network as per the slides you've just been looking at. Input 1 is via that yellow lead there, input 2 via that orange lead there, and the output taken off the blue lead here. All those are connected to various scope channels, and just for completeness, you've got positive supply there, negative supply there, and the zero rail is actually this this bus just running along there. Right, let's look at the scope view. Here's the oscilloscope view then. So I've got the two inputs, which are the yellow and the blue traces here, and currently I've got the same 500 Hertz sine wave being applied to both, and the purple trace is the output of the difference amplifier. Now if you're thinking you need to turn the power on, think again, the power is on, and if you remember the equation that it's input 1 minus input 2 is equal to the output, and since the inputs are identical, if we take one from the other we get 0, so that is exactly what we would expect. But we can verify that because oscilloscope, well, certainly digital scopes have a math menu, or as we prefer to call it on this continental plate, the maths menu, but it is math on this one. So if I set up a math trace on the scope using channels, so using the yellow and the blue channel, and I ask them to subtract, so I'll just switch that on, we'll get that white trace there. So that white trace is the oscilloscope taking the yellow, taking the blue trace away from the yellow trace, and as you can see it concurs exactly with the output of the op-amp on the purple trace. So let's just vary one of those signals and see what we get, and the easiest way to do it initially is to just change the phase of one of those signals so it's out of step. So I'm going to put 90 degrees of phase shift onto channel 1, and you can see the phase shift there between the two channels, 90 degrees. So now we've got an output from the op-amp, and it matches exactly with the output from the math menu on the scope here. So you can see the op-amp is indeed doing the maths, if you like, and taking one signal from another. So if I now just step along that trace in 10 degree steps in phase, so I'm advancing the phase now, and I'll continue right up to that's 160, 170, that's 180. So at 180 degrees, completely out of phase, you can see we've got double the amplitude compared to when the signals were in phase. Okay, so I'll just hop that back to 0, like so, just to verify where we are. So another thing we can do is if we alter the frequency, we'll obviously get a shift. Now I'm actually going to do that particular, just forgive me a moment while I swap between channels. Here we go. I'm going to change the frequency on actually on the blue trace, because I'm triggering off the yellow trace, and hopefully I'll keep the trace stable. This may go horribly wrong, or maybe it won't, we'll just see. So I'm now going to select a 250 Hertz on the blue trace, and let's see what that does. So you can hopefully see now, it's getting a bit confused, so what I'm just going to do there is just pause it so you can make some sense. But you can see we've now got a half, the blue trace is now double the wavelength, or double the period if you like, of the yellow trace, and we've got that maths going on, one being taken through the, so we've got that double peak, and as you can see the math menu produces exactly the same output. So that's it, we've got the op amp doing maths, as we say over here in Europe, and I'm just going to change that frequency back to 500 Hertz, and if I were to just change the frequency in 100 Hertz steps, you can see we'll get all sorts of wacky waveforms. I'm just going to see if I can stop that triggering problem. No, it's going to do it whatever happens. But yeah, you can see as I step up, as I change the frequency of one of the inputs, at any moment in time we get a different output. So I'll just pause that so you can see everything. So we've now got 400 Hertz on the yellow trace, and we've got 500 Hertz on the blue trace, and that gives us that waveform there, and the math menu on the scope completely agrees with that. So there's your op amp doing some maths. On to our next example then, which is the summing amplifier. So here's the general arrangement of the circuit. Now I've shown 3 inputs there, and I've called all the input resistors R1 because they're always the same, but you don't have to have 3, you can have 2 or 7, however many you want. Got the same negative feedback resistor R2 as you've seen in several circuits before, but this time we've got R4 going down to ground. And so the output then of this circuit from a mathematical point of view is the voltage out is equal to voltage in 1 plus voltage in 2, and I've not gone on to show it, but essentially it adds up all the input voltages. So R1, all the R1s, and R2, in this case I'm going to use 10k to give us a unity gain stage, and R4 is going to be 1k. So looking at the breadboard then, pretty straightforward setup. Got the 2 10k input resistors in left and centre, the R2, which is the feedback resistor between the output and the negative going input, is the vertically mounted 10k one, and then we've got the 1k resistor going to ground there on the right hand side. So let's now go and have a look at that on the breadboard. Here's the summing amplifier on the breadboard then. 2 10k input resistors are there. I'm just going to do 2 inputs because I've only got the 2-channel signal generator. That's the resistor that is providing the negative feedback, and that's the 1k resistor to ground from the positive going input. So inputs are here on the yellow and here on the orange, and I'm taking the output trace from the blue line there. So let's look at the scope. Here's the scope view of the summing amplifier then, and currently I've got a 500 millivolt signal on channel 1, and I've got nothing coming in on channel 2, and there's the output of the op amp. As you can see, it agrees with the input. So now I'm going to put 100 millivolts of signal onto channel 2, same frequency and phase as channel 1, and it should add them up. So here's 100 millivolts, and hopefully you could see a change in the size of the trace there. That's off, on, and if I now step that input up through 100 millivolt steps, so 200, 300, 400, 500, you can see the op amp is indeed adding up the two signals. And if I continue, okay, it's going off the scale, but I'm now at 900 millivolts on channel 2 and it's adding it up. So let's just hop back down to 100 again there. Let's engage the maths trace on the scope, and I've got the operator there changed to addition, so you can see the scopes adding up of those two signals agrees with the op amp. And I'll now, because the way I've got it triggered, it appears to be out of phase, but it's actually easier to see that way. So that's 100 millivolts, 2, 3, 4, 5, and you can see the scope takes a moment to do the maths, whereas the op amp is instant. Never let it be said that everything in this world that's fast is digital. You've got an entirely analog maths process occurring on the purple trace, and as you can see, it's instant. Takes the scope a moment or two to do it. Obviously it's got to convert from digital to analog, do the processing and then display it, so can't be too critical really, but just a nice example there of how instantaneous analog can actually be. And if I turn that up to 500 millivolts and switch it, okay, that's off, so we've got 0 on channel 2, and if I switch it on, as you can see, it takes a moment for the digital domain to catch up. Okay, that's the summing amplifier. Okay, you've seen two uses there for the op amp in the signal processing role, producing an output that's mathematically related to the input. Hopefully it's made some sense. When I started this relook at op amps, I was aware it was going to take more than one episode or more than one video to actually cover the topics concerned. This is the second one. There's at least a third, maybe a fourth. We'll just have to see how we go with that. But I hope this one's been useful and you've enjoyed the content. If you're thinking of getting yourself a new multimeter, have a look in the description. You can check out the ones that are on offer by Kaiweets. If you like what you see, I have reviewed them all as well, so you can check out those reviews. If you like what you see and you fancy buying one, there is actually some codes there which allow you to get a discount, which also helps the channel. So if you're thinking of doing that, that'd be great. If you've already done that, thank you very much indeed. That really is appreciated. No cost is to click thumbs up, and also to subscribe. Both of those would be very helpful to me, so I'd appreciate it if you do that, if you don't mind, and we'll look forward to seeing you on the next video.